Hey there everybody, welcome back. So in previous videos, I talked about the center of mass, all right? And in this one, I'll talk about the impulse momentum theorem, and there is a deep, intimate connection between the two. So what I have here is a picture of a hammer being tossed through the air, right? So just at the start, if we look at the hammer itself, right? The center of mass, and I can't show on the screen with my pencil or else this close crop will go away. But where that red line crosses the hammer is the location of the center of mass, right? It's on the handle and just below the head, right? So it's centered horizontally, left to right, but not up and down. Because the head of a hammer, if you haven't held a hammer at all, most of its mass is at the head, right? Because its use is to hammer nails, right? It has to be very heavy up there and sturdy, right? So its center of mass is just below the head, but along the handle axis. And so as you throw the hammer in the air, it turns, but notice that the center of mass, the red dotted line arrow thing, always crosses the hammer at this exact same point, right? On the hammer. Because again, the mass distribution of the hammer is not changing. But not only that, that's not the important thing here. The important thing is to look overall and see that the center of mass's position in space as the hammer is thrown forms a nice, smooth, contrary to what I'm sketching here, a nice smooth parabola in the air, right? So once you throw it and it releases from your hand, the only force on it, aside from air resistance, which is very small, is the force of gravity down, right? And that's the force that's changing its velocity from being initially that to, say, that at the apex, and then later that. So the force of gravity creates its change in velocity, which means that there's some acceleration of the hammer's center of mass. And that acceleration is little g, right? So let's see how that corresponds or connects to the center of mass. So you may remember the center of mass equation has the total mass times what we left off as the speed, or I'll write it as the velocity of the center of mass. So if that happens to change, that must take some time, right? But the rest of the equation was this, okay? And I'm writing this as velocity now, not speed, okay? So if the center of mass moves in space, that has to take some time, right? Well, let's see what happens if this changes, okay? If the velocity changes. Well, you know there should be an acceleration. So let's see where that comes from. To start, on the left, right, this product on the left is what physicists call linear momentum, mass times velocity, or mass times speed. And we denote that by a lowercase p, okay? Linear momentum. So this is the total linear momentum, in this case, of the hammer. And so the picture shown is a bunch of snapshots in time of that hammer. So we can write the total linear momentum is m times v, but it's of the center of mass, right? I don't care what happens to the speed of this bottom point of that handle, right? If you look at it overall, that handle is going woo, 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 like that, right? So that, I'll say linear speed there is much greater than the linear speed of the center of mass, because it's actually moving around in a circle. But I don't care about that. The momentum for this hammer is only worried about the velocity of the center of its mass, okay? So knowing that, what happens if that changes? And that must change for something to be thrown through the air, because again, Initially, it has a velocity. No, you can't see that. Let's do it in blue. Nope. Initially, it has a velocity like this, right? But later, the velocity changes. So there must be an acceleration. So that means we have something like this. We have d dt of this linear momentum, right? And so that means that we have a change in time, so a ddt, of that total mass and the velocity of the center of mass, right? So I'm kind of ignoring this right side for now, and I'm taking a look at just the left side here, okay? So both of these are true now. Let's see what happens. Well, what is the right side? Let's do that first. The mass is not changing, right? As this hammer is tossed through the air, it doesn't break apart. So the mass total is staying constant, right? It turns out that even if the hammer did break into multiple mass chunks, it wouldn't matter. But that's neither here nor there right now. That means we have dv dt, right? And this is where we get our acceleration. So this is the acceleration of the center of mass. Okay? Now let's look at the left side. You see ma, well, that should be equal to a force. Well, we have dp dt, vector, right? And so I'm going to bring this dt, the differential, I'm going to bring that to the other side, okay? So I guess this would be called a separable differential equation. So then we have just dp on the left, and now we're equal to mass. Well, let me just write that as a force, right? The total force times that dt term that we brought over, okay? And since they're differentials, we typically don't like just differentials. We have to integrate both sides, right? So in this case, we might be integrating from, the start of the throw to some final point over here, right? Whatever. But more importantly, this left side, integral dp, well, that's pretty much just the change in linear momentum. And that equals the right side of the force that's staying constant times delta t, right? Times the time through which that force is applied. And this is the impulse momentum theorem right there. It says that if a force is applied to an object, it has to be applied for some time in order to change that object's linear momentum. In other words, it has to be applied for some time in order for that force to change that object's velocity. Okay? So in this case of the hammer, the force is the gravitational force. It's constant. It's an external force, so I should also put external. And it's acting for some time. What time? I don't know. However long it took to go from here over to there. But during that time, its velocity changed, right? From that to that. And thus its linear momentum changed. You can plug in numbers if you want, but just qualitatively, just using equations, this is the impulse momentum theorem. Looking at it another way, we can talk about, say, impacts, right? You can have a very large force applied across a very short amount of time and change the linear momentum the same amount as if you had a very small force applied across a very large time, right? because the right side here is just a product, right? If you increase one side, you have to decrease the other side in order for this to be constant, right? Or decrease and increase for that to be constant. A couple examples. Humans have evolved to have knees that bend, right? And thankfully so, because as we walk, what do our knees do? They bend, right? This helps lessen the force of the impact of the ground on our bodies, right? Or on our individual legs. If it decreases the force of impact, it increases the time that force is applied across, right? Same thing happens when we, say, jump down from some height. If we jump, we land on both feet, and hopefully our knees will bend, right? Or we bend and then roll. What's this effectively doing? Well, we're increasing the time of impact, so we're decreasing the force on our bodies, but we're still having the change in linear momentum occur from whatever it was down to zero, right? And so this decrease in force results in our legs not breaking, right? If we jump down from some height, don't land with your knees locked because you'll break your knees, right? It's a very small time and a very great force, a very large force, right? A few other examples are crumple zones in the fronts of cars, right? In my truck, I actually have a rather large crumple zone than what I've had in the past. It's just space, right? So if anything were to happen, if I were to strike anything with the front of my truck, not only would the airbag deploy, which is another example of this, but the front of my truck would literally crumple, and whatever object I would hopefully have, I may have hit, would take a little bit of more time before it actually hit the engine and thus me, right? Decreasing the force. Other examples I have written down here are the classic egg toss activity, right? If you throw an egg to someone and you want them to catch it without breaking, how do they catch it best? Well, they kind of have to catch it and then move their hands along the direction of the egg traveling, right? They don't just have their hands still and just snatch it out of the air, right? And one more example of the other way is that in order to hit a baseball really far, you want the baseball bat to be as hard as possible, which is why they make baseball bats out of hickory and maple, right? And ash, I guess. Those are very hard woods. They're not made out of styrofoam, right? They're not made out of rubber. They're made out of a hard substance. They want to decrease the time of contact between the bat and ball to increase the force, all right? So these are all examples of the impulse momentum theorem. What are some examples that I didn't mention that you can come up with? All right, thanks for watching.